Hi, this is Johnny with Simpson Math. In this video, we'll be solving some trigonometric equations, and that just means we've got some sort of equation where trig is involved, and I want to solve for the unknown variable. So like in this case, I have cosine of x is equal to 1/2. This is just asking cosine of what angle will give me 1/2, or what can I put into this function, this cosine function, that will output 1/2. So this may sound familiar, especially if you've dealt with the inverse trig functions, but today we're just treating them as old school, like algebra. I'm just solving equations. So if I'm given this situation, cosine of x equals 1/2, I know what values of cosine give me a positive 1/2. I'm going to use the unit circle. I know cosine is positive in quadrants 1 and 4. And cosine is that pretty 1/2 at the pi thirds. So up at pi thirds, and then that'll happen again down here at, let's see, 1, 2, 3, 4, 5 pi thirds. So I kind of want to just say, oh, the answer is pi thirds and 5 pi thirds. That's where this equation is true. But I could continue. I think there's going to be a lot more solutions out there. If I just kind of continue around the unit circle, again at 7 pi thirds, and then something coterminal to 5 pi thirds. Even the negatives, like negative 1 pi third. If I plug in negative 1 pi third into this equation, it's going to hold true. So for these problems today, I'm going to just say, let's just give me all the good values in the first revolution of the unit circle. So I'm really just looking for values in this interval. Let's go from 0 to 2 pi. Now 2 pi is coterminal to 0, so I don't want to include that value twice, or that radian twice. So I'm just going to count 0 up to 2 pi. So in this case, I think I'm done. I know that pi thirds and 5 pi thirds are the only two angles within that first revolution of the unit circle, this interval, that give me an output of positive 1/2. So there's different ways to denote this solution, but because there are several solutions, maybe I'll use this set notation where I'll say, pi thirds works, and so does 5 pi thirds. If I was asked to give all of the solutions, I'd have to be a little more clever with my notation. So I'm going to do it one time for this purpose of this video, but again, for the rest of the video, I'm just going to be using the interval 0 to 2 pi. But if I needed to show pi thirds and then all of its coterminal angles, clockwise and counterclockwise, I would do something like this. I would say, start with that good value, pi thirds, and then I'm going to add to that the distance until I get to that next spot. So this is a full revolution, so I'm going to add a full 2 pi. So I'm going to say plus 2 pi. You could use n for integers. I like to use k. And again, I've got 5 pi thirds, and it will also have a revolution of 2 pi to get to that next good value. So I'm going to add plus 2 pi k. Maybe I'll come off to the side and say, oh, by the way, when I'm talking about k, I'm talking about just an integer. So k is an element of the integers. So this just means if k were 0, the integer is 0, well, that completely destroys this, and I get pi thirds, check mark. If k were the positive integer 1, well, I would do pi thirds plus 2 pi, and I would get that 7 pi thirds. If k was the negative integer, negative 1, then instead I would be subtracting 2 pi. So pi thirds minus 2 pi would be the same value, the same position on the unit circle. All right. So this, I think, would be a good representation for every possible value I could plug in this equation that would make it hold true. All right, let's move on. Let's keep it pretty simple at first. So let's take a look at our next example. Sine of x equals negative root 3 over 2. I know this value as well. That value is on the unit circle. I kind of have memorized that sine is pretty at pi 6. So this is not pretty. So I know that this is going to be those thirds again. But sine is negative in quadrants 3 and 4. Let's see. I'm just going to sketch out the unit circle. The sine value will be that negative root 3 over 2 at this third. So that's 1, 2, 3, 4 pi thirds. And then sine is also negative in quadrant 4. This will be at 5 pi thirds. And those are the only values within the first revolution of the unit circle that make this equation true. So I'm simply going to say what works are the set 4 pi thirds and 5 pi thirds. You may be used to, when solving, getting that x value by itself, so x equals. That would be a fine notation as well. So you could say x equals 4 pi thirds and 5 pi thirds. Either will work. You're just trying to get the point across that these two radians, I can plug into this function and it'll make it true, or keep it true. All right, number 3 has a couple steps. First, I've been given cosine of x plus 2/3 equals 3/2 being raised to a negative first power. Okay, to solve a trig equation, I really kind of need it in that pretty form. I need the trig function to be isolated on its side of the equation. So I'm going to want to move that 2/3 over. But even before I do that, I've got this -1 exponent on the right-hand side. I want to simplify that. So a -1 power simply means I need to reciprocate my base. My base is the fraction 3/2, so when I reciprocate, I'll get 2/3. So I'm just reciprocating -1 exponent. Now I want the trig function by itself, so I'm going to subtract 2/3 from both sides of the equation. It's an equation, so if I subtract on the left, it's fine as long as I do it to the right-hand side as well. So I have cosine x is now equal to, well, that completely goes away, 0. Yeah, in this form, I think I can answer the question. The trig function is isolated. It's equal to some value over here. And I'm today just using my knowledge of trig to answer this question. So I'm supposed to know where cosine is 0. That's on the unit circle. Where is that x value 0? So I like to draw unit circles on every little problem just to make sure my mind is where it needs to be. So cosine is the x value. That's going to happen here at pi halves, and then again at 3 pi halves. Cosine of pi halves is 0. Cosine of 3 pi halves is 0. And these are the only two radians within 0 to 2 pi that make this equation true. So I've got the answer. X equals pi halves and also 3 pi halves. All right, move on to a little bit more challenging problem. Let's look at this fourth one on the board. I have tangent of this phase shift or horizontal shift, x minus pi fourths, is equal to 1. So the trig function has been isolated, the numbers on the other side of the equation, but that x minus pi fourths is kind of throwing me off. So I think for this type of an example, number 4 and 5, when I have that phase shift or there's something going on inside that argument of the trig function, it may be easier to just replace whatever's inside the argument with another dummy variable. So I'll use something like theta. I'm going to let theta equal the argument of this trig function, x minus pi fourths. And then I'm going to rewrite the equation. So now I have tangent of a theta equals 1. And I can answer this question. This is saying, what can I put into tangent that will spit out a positive 1? Tangent is positive 1 in quadrants 1 and 3. It's at those pi fourths. So I'm looking at positive pi fourths and positive 1. I got to draw that circle. Up here in quadrant 1 pi fourth, and 5 pi fourths. Now that's where theta will equal 1. I can go ahead and say that. Theta would be pi fourths, and theta would be 5 pi fourths. But I need that x. So what I'm going to do now is just go back to my equation, my relationship between theta and x, and say, okay, theta is x minus pi fourths. So I have, on the left-hand side here, x minus pi fourths in place of theta is equal to pi fourths. And again with this theta is x minus pi fourths equals 5 pi fourths. So I've created two equations, and I'm going to solve both equations. This left one, I just need to add pi fourths. In fact, on both of them, I just need to add pi fourths to both sides. So if I add pi fourths to pi fourths, I get 2 pi fourths, which reduces, I get pi halves. On the other equation, I'll add pi fourths over. I'll have 6 pi fourths. They have the common denominator, so it's easy to add. And then I can reduce that as well. That's 3 pi halves. Should have written that problem a little lower. Getting kind of messy, but there we go. These two radians, when I plug them into this equation, the equation will hold true. There are an infinite number of solutions, but again, I'm just looking for the solutions within that first interval from 0 to 2 pi. And I can tell that the next one's going to go over 2 pi. All right, my next example. I have 4 sine of x minus pi eighths, and that's equal to the square root of 12. Again, I want to isolate the trig function, so the 4 coefficient needs to be divided off. I think, though, I'll simplify the right-hand side first. I've got the square root of 12. That can simplify. Factors of 12, 4 and 3 will work nicely. So I have the square root of 4 and 3, so I've got 2 square roots of 3. Simplify the radical. Now that coefficient needs to come off the sign. I need to isolate the sine function. So I'm going to take both sides of the equation and divide by 4. I have some reduction on the right I can do. Oh yeah, square root of 3 over 2. I've got this. This is the thirds again. So sine will be positive at pi thirds, and then again at 2 pi thirds. But that's if I had just an x in here. I've got an x minus pi eighths. So again, with this phase shift, or my argument that's not quite just x, I'm going to introduce another variable. I'll use theta again. I'm going to let theta equal this x minus pi eighths. So then I have sine of theta equals the root of 3 over 2. And now I can answer that question. Theta would be pi thirds, and theta would be 2 pi thirds. That would make this equation true. Ooh, but theta is x minus pi eighths. So I'll go back and I'll take my theta and say, hey, that was x minus pi eighths. And I kind of like to do these at the same time. The theta is going to be the same thing, x minus pi eighths. It's equal to 2 pi thirds. And I'm going to just solve these equations basically at the same time. As I add pi eighths over, I know I'm going to need a common denominator. So I'm going to do 2 steps in one. I'm going to move the pi eighths to the other side of the equation, and I'm going to get a common denominator. 3 and 8 looks like 24. So if I'm going to change pi thirds into 24ths, I'll have 8 pi 24ths. And I'm adding over pi eighths, but I'm going to change that into 3 pi 24ths. Similarly, on this other equation, I need to get a common denominator. So 2 pi thirds will become 16 pi 24ths. I'm adding 3 pi 24ths. Now that I have the common denominator, I can add and I'll be done. 8 and 3 is 11. So one possible solution is 11 pi 24ths. Another solution would be 19 pi 24ths. You can box it as is. If you want to use set notation, that's fine. You could say the set, and typically we do it in like an increasing order, ascending order. So I'll just say 11 pi 24ths, comma, 19 pi 24ths. All right, so these two solutions, when I plug them back into the original equation, this equation will hold true. I hope that makes some sense. In my next video, I'm going to do maybe like 5 more examples, but get a little bit more tougher, a little harder. All right.